Water hammer is a pressure surge or wave caused when a fluid in motion is forced to stop or change direction suddenly. A water hammer commonly occurs when a valve closes suddenly at an end of a pipeline system, and a pressure wave propagates in the pipe. It is also called hydraulic shock. This pressure wave can cause major problems, from noise and vibration to pipe collapse. It is possible to reduce the effects of the water hammer pulses with accumulators, expansion tanks, surge tanks, and other features. Rough calculations can be made either using the Joukowsky equation, or more accurate ones using the method of characteristics. Cause and effect. When a pipe is suddenly closed at the outlet, the mass of water before the closure is still moving, thereby building up high pressure and the resulting shock wave. In domestic plumbing, this is experienced as a loud banging, resembling a hammering noise. Water hammer can cause pipelines to break if the pressure is high enough. Air traps or standpipes are sometimes added as dampers to water systems to absorb the potentially damaging forces caused by the moving water. In hydroelectric generating stations, the water traveling along the tunnel or pipeline may be prevented from entering a turbine by closing a valve. However, if, for example, there is 14 kilometers of tunnel of 7.7 meters diameter, full of water traveling at 3.75 meters per second, that represents approximately 8,000 megajoules of kinetic energy that must be arrested. This arresting is frequently achieved by a surge shaft open at the top, into which the water flows. As the water rises up the shaft, its kinetic energy is converted into potential energy, which decelerates the water in the tunnel. At some HEP stations, what looks like a water tower is actually one of these devices, known in these cases as a surge drum. In the home, water hammer may occur when a dishwasher, washing machine, or toilet shuts off water flow. The result may be heard as a loud bang, repetitive banging, or as some shuddering. On the other hand, when an upstream valve in a pipe closes, water downstream of the valve attempts to continue flowing, creating a vacuum that may cause the pipe to collapse or implode. This problem can be particularly acute if the pipe is on a downhill slope. To prevent this, air and vacuum relief valves, or air vents, are installed just downstream of the valve to allow air to enter the line for preventing this vacuum from occurring. Other causes of water hammer are pump failure and check valve slam. Related phenomena. Steam distribution systems may also be vulnerable to a situation similar to water hammer, known as steam hammer. In a steam system, water hammer most often occurs when some of the steam condenses into water in a horizontal section of the steam piping. Subsequently, steam picks up the water, forms a slug, and hurls it at high velocity into a pipe fitting, creating a loud hammering noise and greatly stressing the pipe. This condition is usually caused by a poor condensate drainage strategy. Where air-fill traps are used, these eventually become depleted of their trapped air over a long period of time through absorption into the water. This can be cured by shutting off the supply, opening taps at the highest and lowest locations to drain the system, and then closing the taps and reopening the supply. Water hammer during an explosion. When an explosion happens in an enclosed space, water hammer can cause the walls of the container to deform. However, it can also impart momentum to the enclosure if it is free to move. An underwater explosion in the SL-1 nuclear reactor vessel caused the water to accelerate upwards through 0.76 meters of air before it struck the vessel head at 49 meters per second with a pressure of 680 atmospheres. This pressure wave caused the 12,000 kg steel vessel to jump 2.77 meters into the air before it dropped into its prior location. Mitigating measures. Water hammer has caused accidents and fatalities, but usually damage is limited to breakage of pipes or appendages. An engineer should always assess the risk of a pipeline burst. Pipelines transporting hazardous liquids or gases warrant special care in design, construction, and operation. Hydroelectric power plants especially must be carefully designed and maintained because the water hammer can cause water pipes to fail catastrophically. The following characteristics may reduce or eliminate water hammer. Reduce the pressure of the water supply to the building by fitting a regulator. Lower fluid velocities. To keep water hammer low, pipe sizing charts for some applications recommend flow velocity at or below 1.5 meters per second. Fit slowly closing valves. Toilet fill valves are available in a quiet fill type that closes quietly. High pipeline pressure rating. Good pipeline control. Water towers help maintain steady flow rates and trap large pressure fluctuations. Air vessels work in much the same way as water towers, but are pressurized. They typically have an air cushion above the fluid level in the vessel, which may be regulated or separated by a bladder. Sizes of air vessels may be up to hundreds of cubic meters on large pipelines. They come in many shapes, sizes and configurations. Such vessels often are called accumulators or expansion tanks. A hydropneumatic device similar in principle to a shock absorber called a water hammer arrestor can be installed between the water pipe and the machine to absorb the shock and stop the banging. Air valves often remediate low pressures at high points in the pipeline. Though effective, sometimes large numbers of air valves need be installed. These valves also allow air into the system, which is often unwanted. Shorter branch pipe lengths. Shorter lengths of straight pipe, i.e., add elbows, expansion loops. Water hammer is related to the speed of sound in the fluid, and elbows reduce the influences of pressure waves. Arranging the larger piping in loops that supply shorter, smaller run-out pipe branches. With looped piping, lower velocity flows from both sides of a loop can serve a branch. Flywheel on pump. Pumping station bypass. The magnitude of the pulse. One of the first to successfully investigate the water hammer problem was the Italian engineer Lorenzo Alliva. Water hammer can be analyzed by two different approaches: rigid column theory, which ignores compressibility of the fluid and elasticity of the walls of the pipe, or by a full analysis that includes elasticity, when the time it takes a valve to close is long compared to the propagation time for a pressure wave to travel the length of the pipe. Then rigid column theory is appropriate, otherwise considering elasticity may be necessary. Below are two approximations for the peak pressure, one that considers elasticity, but assumes the valve closes instantaneously, and a second that neglects elasticity but includes a finite time for the valve to close. Instant valve closure, compressible fluid. The pressure profile of the water hammer pulse can be calculated from the Joukowski equation. So for a valve closing instantaneously, the maximum magnitude of the water hammer pulse is, where delta P is the magnitude of the pressure wave, ρ is the density of the fluid, A0 is the speed of sound in the fluid, and delta V is the change in the fluid's velocity. The pulse comes about due to Newton's laws of motion and the continuity equation applied to the deceleration of a fluid element, where R equals wave speed, B equals equivalent bulk modulus of elasticity of the system fluid pipe, ρ equals density of the fluid, K equals bulk modulus of elasticity of the fluid, E equals elastic modulus of the pipe, D equals internal pipe diameter, T equals pipe wall thickness, C equals dimensionless parameter due to system pipe constraint condition on wave speed. Slow valve closure. Incompressible fluid. When the valve is closed slowly compared to the transit time for a pressure wave to travel the length of the pipe, the elasticity can be neglected, and the phenomenon can be described in terms of inertance or rigid column theory, assuming constant deceleration of the water column, gives, where F equals force, m equals mass of the fluid column, kilogram, r equals acceleration, meter per square second, p equals pressure, par, r equals pipe cross-section, m2, ρ equals fluid density, kilogram per cubic meter, l equals pipe length, v equals flow velocity, meter per second. T equals valve closure time. The above formula becomes, for water and with imperial unit, P equals 0.0135 VL/T. For practical application, a safety factor of about 5 is recommended, where P1 is the inlet pressure in psi, V is the flow velocity in FD, sec, T is the valve closing time in seconds, and L is the upstream pipe length in feet. Expression for the excess pressure due to water hammer. When a valve with a volumetric flow rate Q is closed, an excess pressure delta P is created upstream of the valve, whose value is given by the Joukowski equation. In this expression, overpressurization delta P is expressed in par. Q is the volumetric flow in cubic meter per second. Z is the hydraulic impedance, expressed in kilogram per meter 4 per second. The hydraulic impedance Z of the pipeline determines the magnitude of the water hammer pulse. It is itself defined by, with ρ the density of the liquid, expressed in kilogram per cubic meter, a cross-sectional area of the pipe, M2. The equivalent modulus of compressibility of the liquid in the pipe, expressed in par. The latter follows from a series of hydraulic concepts. Compressibility of the liquid, defined by its adiabatic compressibility modulus BL, resulting from the equation of state of the liquid generally available from thermodynamic tables. The elasticity of the walls of the pipe, which defines an equivalent bulk modulus of compressibility for the solid Bs. In the case of a pipe of circular cross-section whose thickness T is small compared to the diameter D, the equivalent modulus of compressibility is given by the following formula, in which E is the Young's modulus of the material of the pipe, possibly compressibility Bg of gas dissolved in the liquid, defined by gamma being the specific heat ratio of the gas, alpha the rate of ventilation, and P the pressure. Thus, the equivalent elasticity is the sum of the original elasticities. As a result, we see that we can reduce the water hammer by increasing the pipe diameter at constant flow, which reduces the flow velocity and hence the deceleration of the liquid column. Employing the solid material as tight as possible with respect to the internal fluid bulk. Introducing a device that increases the flexibility of the entire hydraulic system, such as a hydraulic accumulator, where possible, increasing the percentage of undissolved gases in the liquid. Dynamic equations. The water hammer effect can be simulated by solving the following partial differential equations, where V is the fluid velocity inside pipe, is the fluid density, and B is the equivalent bulk modulus, F is the friction factor. Column separation. Column separation is a phenomenon that can occur during a water hammer event. If the pressure in a pipeline drops below the vapor pressure of the liquid, cavitation will occur. This is most likely to occur at specific locations such as closed ends, high points or knees. When the pressure later increases above the vapor pressure of the liquid, the vapor in the bubble returns to a liquid state, which leaves a vacuum in the space formerly occupied by the vapor. The liquid either side of the vacuum is then accelerated into this space by the pressure difference. The collision of the two columns of liquid causes a large and nearly instantaneous rise in pressure. This pressure rise can damage hydraulic machinery, individual pipes and supporting structures. Many repetitions of cavity formation and collapse may occur in a single water hammer event. Simulation software. Most water hammer software packages use the method of characteristics to solve the differential equations involved. This method works well if the wave speed does not vary in time due to either air or gas entrainment in a pipeline. The wave method is also used in various software packages. WM lets operators analyze large networks efficiently. Many commercial and non-commercial packages are available. Software packages vary in complexity, dependent on the processes modeled. The more sophisticated packages may have any of the following features: multi-phase flow capabilities, an algorithm for cavitation growth and collapse, unsteady friction, the pressure waves dampens as turbulence is generated and due to variations in the flow velocity distribution. Varying bulk modulus for higher pressures. Fluid structure interaction, the pipeline reacts on the varying pressures and causes pressure waves itself. Applications. The water hammer principle can be used to create a simple water pump called a hydraulic ram. Leaks can sometimes be detected using water hammer. Enclosed air pockets can be detected in pipelines. History. Water hammer was exploited before there was even a word for it. In 1772, Englishman John Whitehurst built a hydraulic ram for a home in Cheshire, England. In 1796, French inventor Joseph Michel Montgolfier built a hydraulic ram for his paper mill in Voiron. In French and Italian, the terms for water hammer come from the hydraulic ram. Coup de Bel-Air and colpo de rietor both mean blow of the ram. As the 19th century witnessed the installation of municipal water supplies, water hammer became a concern to civil engineers. Water hammer also interested physiologists who were studying the circulatory system, although it was prefigured in work by Thomas Young. The theory of water hammer is generally considered to have begun in 1883 with the work of German physiologist Johannes von Kreis, who was investigating the pulse in blood vessels. However, his findings went unnoticed by civil engineers. Kreis's findings were subsequently derived independently in 1898 by the Russian fluid dynamicist Nikolai Yegorovich Zhukovsky. In 1898 by the American civil engineer Joseph Palmer Frazal, and in 1902 by the Italian engineer Lorenzo Alliva.